My name is Ryan Urbanowitz, and I'm an assistant professor of computational biomedicine at the Cedars-Sinai Medical Center, an adjunct assistant professor of the University of Pennsylvania Informatics Department, director of the Cedars AI Campus Program, and co-lead of the Technology Identification and Training Core for Penn AI Tech. My lab's research is focused on the development and application of machine learning and artificial intelligence methods, tools, and software geared towards the myriad challenges investigators face when analyzing different biomedical data sets. Today I'm going to talk briefly about automated machine learning and the adoption of best practices in data science. Biomedical data collected to study any number of disease outcomes, including Alzheimer's disease and related disorders, comes in many forms, including structured data from omics and electronic health records, as well as images, time series data, and unstructured text, such as doctor's notes. Given this potentially large, noisy, and complex pool of patient features, one of the most common goals motivating the application of machine learning is to discover, predict, and understand the relationships between these features and disease outcomes. These relationships could be simple univariate associations, or involve many features in a much more complex way. For example, feature interactions, otherwise known as epistasis. This general task is often all the more difficult in biomedical research, where the data is often of a large scale, noisy, complex, includes rare variation in some features, and where there is a need for models to be transparent, interpretable, and explainable rather than just opaque. It's not uncommon for those who are new to machine learning and data science to potentially underestimate how difficult it can be to not only set up an analysis pipeline, but to do so in a way that avoids assumptions, bias, and mistakes that can undermine our downstream conclusions. This schematic gives a high-level look at some of the many common elements found in a machine learning analysis pipeline. Every individual element here can be approached using a wide variety of methodological options, each with their own advantages and disadvantages. In designing an analysis pipeline for a given dataset or problem, decisions need to be made regarding what elements to include, the order that they're applied, and how to ensure that best practices in data science and machine learning are being correctly applied. If you'd like to learn more about these data science pipeline elements, you can check out our lab's YouTube channel, including this web link to a playlist on machine learning essentials for data science, which can also be found through the Penn AI's website's resources page. So given these analytical challenges, a new subfield of artificial intelligence and machine learning has emerged called automated machine learning, or AutoML. This field focuses on automating the design or application of elements of a machine learning analysis pipeline. Ultimately, the goal of AutoML is to make machine learning easier to apply and more accessible even to investigators without programming experience, and at the same time seek to improve the performance of the models that are trained. To date, 2 to 3 dozen enterprise and open source AutoML tools and libraries have been proposed, each with their own scope, strengths, and limitations. Among these is an AutoML called Streamline, developed by our research group. Summarized in this schematic, Streamline is a simple, transparent, end-to-end automated machine learning pipeline designed as a rigorous, open source, and easy-to-use tool that strictly adheres to best practices in data science, as well as focuses on biomedical data applications. Streamline seeks to automate any data science elements that can be reliably automated without specific domain expertise, including exploratory data analysis, data and feature processing, machine learning modeling using both well-known and cutting-edge machine learning algorithms, comparative evaluations with statistical significance evaluation, replication analysis, and even generating figures and summary reports. The ongoing improvement and expansion of Streamline has benefited from a number of collaborative applications in biomedicine, including the prediction of oncology patient readmission, Alzheimer's disease, cancer early detection, and obstructive sleep apnea, just to name a few. And if you want to try a demonstration of Streamline, the QR code on the left will open a Google Colab notebook to analyze a small, publicly available hepatocellular carcinoma dataset by clicking first on the 3 lines, then selecting Runtime, and lastly Run All. And if you'd like to learn more about Streamline, including instructions for installation and use, or if you'd just like to learn more about AutoML in general, feel free to check out the Streamline YouTube playlist with a QR code on the right. These resources can also be found through the PenAI Tech website's resources page. Thanks so much for watching. If you want to learn more about AutoML, Streamline, or the biomedical applications we mentioned, please feel free to visit the PenAI Tech website or reach out to us directly.